14th. Tonight's agenda, we'll talk about what's due like we normally do. We'll talk about specifically the parable of the bacteria lab, kind of an interesting little lab. And then a couple other announcements I wanted to make that we are currently in registration for summer and fall. So if you have 30 or more credits, you can register either today or tomorrow for summer and fall. And also, if you have less than 30 credits, you can register the rest of this week and next week. So a couple of things that are different. We're registering for both summer and fall, and you can actually register during this first week as well. You can't, it's not like it was before where it was early advising. You'd have to wait till the week after to register. You can actually get put into classes this week as well. So if you're planning on taking any summer and fall classes, you might want to consider early registering. If you're planning on taking any summer classes that may fill up, which sometimes they do, and summer classes are more limited in their offerings, you may want to consider signing up early for summer classes as well. And we have about 4 weeks or so left in the class, which is a good thing, I think. We have one more unit after this unit on consumer finance, which is a pretty good unit. We're going to do a lot with Excel in that section when we talk about loans, house loans, car loans, amortization tables. So there will be an expectation that you can do Excel on that unit. All right, so we'll tackle that when we get there. So what's due for this week? We have section 3.2 that's due on Thursday. Usually it's due Wednesday, but I pushed it back to Thursday because I finally got this video for 3.2 posted today. So I just made a short little video on 3.2 exponential growth and decay. Make sure you watch that before you do section 3.2. The lab, the parable of the bacteria lab is due on Friday, what we're going to talk about tonight. That's our main topic of discussion. And then your Unit 3 test is due on Sunday. I hope to start posting things from Unit 4 this week. All right. So let's just go ahead and talk. So we talked about what we're going to talk about tonight. We're talking about what's due this week. Let's just talk about this lab. And of course, with all labs, you want to show your work and reasoning. This one has a little bit more reasoning to it, I think, than other labs had. Interesting little story, probably a familiar story to some of you. It says, once upon a time, at precisely 11 p.m., a single bacterium was placed in a nutrient-filled bottle in the laboratory. The bacterium immediately began gobbling up nutrients, and just after 1 minute, making the time 11:01 p.m., it had grown so much that it divided into two. So the one became two. These two ate until 1 minute later. They each divided into two, so there were a total of 4. So just to help us out here, 11 p.m. there was 1. It started eating in double. So 11:01 p.m. there was 2. 11:02 p.m. there was 4, and so 11:03 and so on. You get the idea here. There was 8. Let's just do a couple more. 16, and then 11:05, 32, and so on. So you get the idea. It says, all seemed fine, and the bacteria kept on eating happily and doubling their numbers every minute until the midnight catastrophe. The catastrophe was this. At the stroke of 12 a.m., midnight, the bottle became completely full of bacteria with no nutrients remaining, which meant that every single one of the bacteria was suddenly doomed to death. All right, so it was filled up. There was no food left. Question number 1, the catastrophe occurred because the bottle became completely full at 12 a.m. midnight. What time was the bottle half full? So I would strongly encourage you not to do like we did here and work forwards. I would say, well, if it's full, I would start at the bottom here. I say if it's full at 12 a.m., it's full, when is it half full? Start working backwards and use the fact that it doubles every minute. All right, so if it's full at 12 a.m., when is it half full? You can plug numbers in there if you want and try to figure it out, but I think you should be able to figure it out from the verbiage that you're given here. But my hint on this one and on the next one is to work backwards. So question 2, it says you're a mathematically sophisticated bacterium, and at 11:56 you recognize the impending disaster. You immediately jump on your soapbox and warn that unless your fellow bacteria slow their growth dramatically, the end is just 4 minutes away. Will anyone believe you? Give reasons for your conclusions to this question. Consider how the situation might appear to your less mathematically sophisticated friends. So what you need to do to justify this, you know at midnight it's full. If you work yourself backwards, until 11:56 p.m., determine, what part of it, how full is it here? And depending on what your answer is, you might say, well, it's 90% full, then they probably would believe you. But if it's like, 25% full, they might not. So figure out, working backwards, like we talked about. If it's full at midnight, 1 minute before that it is, and then a minute before that, or 2 minutes before midnight, what fraction is it full? And just continue to work yourself backwards. And based on your answer to this, you can go ahead and says, give reasons for your conclusion to this question. Consider how the situation might appear to your less mathematically sophisticated friends. All right. The idea of this whole lab is how quickly things, if you're doubling things, how quickly they add up, how quickly they multiply, if you will. This exponential growth, things grow quickly. All right, and that's the whole purpose of this, to realize how quickly they grow. And even though you're 4 minutes away from impending doom, it may not be obvious that it's impending doom yet. All right. And that's really what it's getting to. Now, turning it over to question number 3, it says it's now 11:59 p.m., so we're right here. So in question 1, you already determined how full it was, 11:59 p.m. You and your fellow bacteria are finally taking your warnings seriously. Hoping to avert an impending doom, they quickly start a space program sending little bacterial spaceships out into the lab in search of new bottles. To their relief, they discover the lab has 3 more bottles that are filled with nutrients but have no one living in them. They immediately commence a mass migration through which they successfully redistribute the population evenly among 4 bottles. The 3 new ones plus the one already there. So we know we already have 1 bottle there, and then we have 3 new ones, all the same size. How much more time does the additional bottles buy for civilization? Or similarly, the midnight catastrophe will now have been pushed back to what time? Well, so they do this at 11:59. You know what fraction full it is, and that's when you're answering these questions like 1 and 2, that's how you want to answer. You don't want to say there's 29 bacterium in there. There's a lot more than that. You want to say it's, a fraction full. All right, whatever. It's not going to be completely full until midnight, but you want to say it's like, an 1/8 full or 3/5 full or something like that, whatever it is. But it's a fraction amount of how full it is. All right. So you should know at 11:59 when they find these extra bottles how full it is there. All right. So what you want to distribute that, however much it is, you want to distribute it equally to the 4 bottles. So I know whenever I have whatever it is, if I want to distribute it equally the amount, whatever it is, I just divide it by 4. And that will work for this case as well. Make sure you give your explanation of, how much more time does that buy? Okay, then the last question, let me just go to the next page here. It says, because the 3 extra bottles bought so little time, so they kind of tell you that it hardly bought any time at all, the bacteria kept searching out more and more bottles. Is there any hope that the additional discoveries will allow the colony to continue its rapid growth? In seeking to answer this question, assume each bacterium occupies a volume of 10 to the negative 21st cubic meters, and that the surface of the Earth is about 500 million square kilometers. If the rate of growth of population continued with no change whatsoever, how deep would the bacteria be spread evenly over the Earth's surface at 1 a.m.? Hint, first consider how many bacteria would be present at 1 a.m. So first they just tell you to do, well, figure out how much bacterium is present at 1 a.m. And 1 a.m. is exactly, this is 120 minutes past 11 a.m. or 11 p.m. I should say. Now, you should be able to come up with an exponential model for this and determine exactly how many bacteria there are at 1 a.m., after 120 minutes. Okay, so determine that first. Again, you can probably figure out an exponential model. Determine volume of all the bacteria, and there's going to be a lot of them. It tells you how big one is. It says, assume each bacterium occupies a volume of 10 to the negative 21st cubic meters. So if one bacterium is 10 to the negative 21st cubic meters, to figure out how many 2 is, you just multiply by 2. You figure out how many 10 is, you just multiply by 10. To figure out how many there is in part, once you do step 1, you just multiply them together. And that gives you how much of a volume it is. All right? So, and it's going to be a big number. It's going to be a big number, I'm not going to lie. Now, the next thing it says that you need to do, it says, how deep would the bacteria be spread evenly over the Earth's surface? So this is the volume of all the bacteria in step number 2. All right? So you're spreading that like a bunch of snow. Think of snow. You're spreading that over the Earth's surface. So, and I need to go to another page here. So if you're spreading that over to the Earth's surface, the volume of all bacteria. You just figured that out in part 2. Okay, that's the second thing you figured out. Part 1, you figured out how many there are. In part 2, it's told you how big one was, so you multiply to figure out how big they are, and that's the volume. And what you want to do is you want to divide that by the volume, or the Earth's surface. They tell you how big the Earth's surface is. So it says the Earth's surface is about 500 square kilometers. Now be careful. This number here that you got, the volume of all bacterium, it's going to be in cubic meters, and the volume of the Earth, or the surface area, the Earth's surface, is about 500 million square kilometers. You see how we have kilometers and meters here? You need to make that the same. You need to make them both meters is what I would do. So I would use the fact that let me think. So 1 kilometer is 1,000 meters. So 1 square kilometer, if I square the 1 square kilometer is equal to 1,000 square meters. Or 1 square km is equal to 1,000 squared is 1,000,000 square meters. I would use this fact right here, convert the Earth's surface into square meters. And that way, when you're dividing the same units. Okay? So this last problem is a little bit more involved. First, you have to figure out how many bacterium is present at 1 a.m., which is exactly 2 hours or 120 minutes past 11 a.m. when they started doing this Dublin trick. And it's going to be a lot, and it's going to be a large number. All right, it's going to be a very large number. It's going to be in scientific notation, which is okay. And then in part 2, it says you have to figure out, or I told you to figure out the volume of all the bacterium. It gives you in the problem that one bacteria is that big. So using that information, you have to figure out what the volume is of all of them. And then part 3 says if that's spread over the Earth's surface, evenly over the Earth's surface, what is the height? How deep is it when you spread? So you want to use what you found in part 2, the volume of all the bacteria, which you just found in the second part of that question, divided by how big of an area that you're spreading it over the Earth's surface. And yeah, I caution you because when you figured out the volume of all the bacterium, it was in cubic meters. Okay, so that was in cubic meters, but yet the Earth's surface they give you that information that says it's 500 million square kilometers. Okay, so there's a little bit of a conflict here, so you got to make them. I suggested to make that square meters using that conversion. And it's going to be pretty high. It's not going to be real high. You know, it's something that's going to be over your head, but not by a lot, you know. Okay, so that's all I got for this lab. Again, I would encourage you to develop a little model for that, for the first part in question number 4. And whenever something doubles, it increases by 100%. All right, I'll give you that hint as well. When something doubles, it increases by 100%. So if you go from 3 to 6, that's actually a 100% increase. From 3 to 6, it's an increase of 3, which was your original amount, so it's a 100% increase. Okay, well, please let me know if you have any questions on that or anything else. You got the 3-2 coming up, the exponential growth and decay models. I did a nice little video on that, and then we got this lab coming up, and then your test this weekend. Let me know. Thank you very much.